today's goal of this lecture. Today I will see some tests for uniform convergence of sequence of function. Just as a review, this is today's goal of this lecture because this topic test for uniform convergence of sequence of function. This topic actually very important for higher study, also for any competitive exam. Okay. So today I will discuss some test which is very important, and in my previous video I had discussed this test elaborately. Today I will discuss this test just as a review. First powerful test is MN test. We all of us know the MN test. In my previous video I had discussed this test. Also I had solved many questions by MN test. See the playlist of my sequence of function playlist. The name of the playlist is sequence of function. There are many various type of video about test for uniform convergence for sequence of function, and today actually I will discuss just as a review. We all of us know MN test. Let Fn be defined on the set A and limit n tends to infinity Fn x equal to Fx. That means Fn converges on the set A to A pointwise. If define Mn equal to supremum x belongs to A, absolute value of Fn x minus Fx, then we can tell Fn converges to F uniformly. And Fn converges to F uniformly if this Mn limit n tends to infinity Mn equal to 0. If this Mn equal to 0, then we can tell the sequence of functions converges uniformly. This is the MN test, we all of us know. Actually, another theorem, consequence of MN test, by this theorem we can just break any sequence of function be uniform convergence or not. This is very shortcut theorem. By this theorem we can break easily a sequence of function be uniformly converges or not. The theorem is, let D be subset of R and Fn and A be two functions which is defined on the set D. If we have a sequence xn in D such that absolute value of Fn xn minus f of xn tends to C as n tends to infinity, where this C is not equal to 0, then the sequence of function Fn does not converges to F on the set D. Okay. By this theorem we can break any sequence of function be uniform convergence or not. If there exists a sequence xn in D such that absolute value of Fn xn minus f of xn tends to C as n tends to infinity and C not equal to 0. Next example, Dini's theorem. We all of us know. Actually, see the playlist, there are separate video about Dini's theorem and many various type of example I have solved by this theorem. This is very easy theorem, but can easily solve any sequence of function. The Dini's theorem is, let A subset of R such that the set A is compact if the sequence Fn converges to F such that For all alpha belongs to A, the sequence Fn alpha is monotonic. Then the sequence Fn is continuous on the set A. Next, F is continuous on the set A. If these three conditions hold, then by Dennis theorem we can tell Fn converges to A uniformly if the sequence is monotone. That means either monotone increasing or monotone decreasing. If the sequence of function Fn is continuous and F is also continuous, then we can tell by Dennis theorem Fn converges to F uniformly. By this theorem, we can construct any sequence of function which is uniform convergent. Another theorem is by differentiability. The theorem is let D subset of R and Fn be sequence of differentiable function on the set D. Let the sequence Fn dash x converges uniformly to a function f on the set D and the sequence Fn converges pointwise for at least one x belongs to D, then the sequence Fn converges uniformly to some function f on the D and f dash x equal to actually gx. That means if Fn be sequence of differentiable function on the set D and if Fn dash converges uniformly to a function f on the set D and Fn converges pointwise, Fn converges to f pointwise for at least one x belongs to D and Fn dash converges to f dash, consider this is converges to z dash uniformly, then we can tell Fn converges to f uniformly and this f dash equal to always g. This is very useful theorem. By this theorem we can also evaluate any sequence of function be uniform convergence or not. Next I will see some example by Mn test. Only I will see some example because this type of example I have solved by Mn test in my previous video. Actually today's video just as a review part. Now I will see couple of example of Mn test. First example this which I had discussed elaborately in my previous video of Mn test. We all of us know. Actually today's video actually just as a review. Today actually I have joined it all question together. First question, if nx equal to nx over 1 plus n square x square, this is does not converges uniformly on 0 1. Here apply for this am greater than gm on the element 1 over nx and nx. Then I will get nx over 1 plus n square x square less than equal to half. Here this is the mn. That means mn greater than equal to half less than equal to half. Here that imply mn equal to half. That means supremum value that does not converges to 0. So this sequence of function does not converges uniformly on closed interval 0, 1. But this function does not converges on 0, 1. But this sequence of function x over 1 plus nx square, this is converges uniformly on the closed interval 0, 1. For this, here also apply am greater than equal to gm on the element 1 over x comma nx. If we apply m greater than equal to gm, then I will get on the element this sequence of function x over 1 plus n square x square less than equal to 1 over 2 square root of n. That means for all x belongs to closed interval 0, 1, this is the mn. That means mn greater than equal to this and less than equal to this. That means mn equal to this is, and as n tends to infinity, mn goes to 0. So this sequence of function converges, since mn goes to 0, converges uniformly on the closed interval 0, 1. Next, consider this sequence of function fnx equal to n plus x squared. This is the converges uniformly because this is the f1, this is f2, this is f3. Notice this sequence of function be monotone decreasing. Here fn goes to 0. Since this is the monotone decreasing, mn equal to supremum of x over n plus x squared. That means here, since this function sequence of function be monotone decreasing sequence of function, so maximum value exists at the point 0. That means if you put this value 0, so that imply mn goes to 0. Since mn goes to 0, so we can tell easily this function converges uniformly on closed interval 0, 1. Notice these three function. Again, okay. Next, consider the sequence of function x to the power n times 1 minus x. This is converges uniformly on the closed interval 0, 1. Since x lies between open interval 0 to 1, so obviously this sequence of function x to the power n times 1 minus x tends to 0. Here mn equal to supremum x to the power n 1 minus x such that x belongs to 0, 1. That means supremum of this sequence of function. And obviously this is the fnx. To find the supremum, we have to find fn dash x equal to 0. And this value is n over n plus 1. Just put the value in mn. Then I will get, this is the value of mn. Apply limit both sides, then this would be, this value we all of us know this is the e, and this value would be 0. And e times 0 equal to 0. That means this sequence of function, since mn tends to 0, so this sequence of function converges uniformly on the closed interval 0, 1. But if we consider this sequence of function nx times 1 minus x to the power n, this does not converges uniformly on closed interval 0, 1. Because since x lies between open interval 0, 1, that means 1 minus x, this is lies between open interval 0, 1. If we consider the sequence of function nx times 1 minus x to the power n, and the supremum value, since fn converges to 0, then mn equal to supremum this function, and since x belongs to close interval 0, 1, so the supremum value would be, since 1 over n belongs to close interval 0, 1, so mn always strictly greater than equal to n times 1 over n times 1 minus 1 to the power n to the power n, and this value is, just cancel this part, this value is, apply limit both sides, then this value is 1 over e. Since limit mn does not tends to 0, so this function does not converges uniformly on the closed interval 0, 1. Now I will see one example which had come in CSR net example, but this example is very conceptual. For n greater than equal to 1, the sequence of function which is defined from open interval 0, 1 to 0, 1, defined by fn x equal to x to the power n, is it uniform convergent? Notice here fn defined from 0, 1 to 0, 1, and fn x equal to x to the power n. Since obviously this part greater than tends to 0, since x lies between 0 to 1, that means fn converges pointwise at the function f equal to 0. Now we have to find is this convergence is uniform. For this I will use the subsequence convergence for uniform convergency. If subsequence convergence is, if we find one sequence xn in the domain such that absolute value of f of xn minus f of n xn minus f of xn tends to c as n tends to infinity, where c does not equal to 0, then fn, the sequence of function, does not converges to f on the domain D. Here I will use actually this rule. Consider the sequence n equal to 1 minus 1 over n. Then fn x equal to, here obviously x to the power n, and fx equal to 0. Then if we put this sequence here, then this value is 1 minus 1 over n to the power n, and as limit n tends to infinity, this value, limit n tends to infinity, 1 minus 1 over n to the power n, this value tends to E inverse. Since this is does not converges to 0, so this sequence of function fn x equal to x to the power n does not converges uniformly to the function f equal to 0. So here as indicate is uniform convergent. This is the wrong option. Second, for n greater than equal to 1, the sequence, this is also defined from open interval 0, 1 to 0, 1. Here the sequence of function x to the power n over log n plus 1. Is it uniform convergent? This is the fn x, and x lies between open interval 0, 1. Since x less than 1, so obviously limit n tends to infinity, fn x tends to 0, pointwise. Now we have to find, is this convergence is uniform? For this I will apply the MN test, which is supremum x belongs to open interval 0 1 fn x minus fx, and this value is supremum x belongs to open interval 0 1 x to the power n over log n plus 1. Okay, and since x less than 1, so obviously x to the power n over log n plus 1, this value less than 1 over log n plus 1. So obviously this value is 1 over log n plus 1, and as n tends to infinity, this value obviously tends to 0. So since mn tends to 0 as n tends to infinity, so obviously this sequence of function converges uniformly at the point at the function fx equal to 0. So option 2 is a right option, and option 3 imply for n greater than equal to 1, the sequence of function which is also defined from open interval 0 1 to 0 1 fn x equal to x to the power n over 1 plus x to the power n. Is it uniform convergent? Since x belongs to open interval 0 1, so this value tends to 0 and this value tends to 0, x to the power n, and this is tends to 0. So fn x converges pointwise to f equal to 0 function. Now we have to check, is this convergence is uniform? For this, consider the, here also I will use the sequence subsequence test. Consider this sequence 1 minus 1 over n, then fn an minus f of an, this value would be 1 minus 1 over n to the power n divided by 1 plus 1 minus 1 over n to the power n, and this value is equal to 0. And as limit n tends to infinity, this value obviously tends to E inverse, also this value tends to E inverse as limit n tends to infinity. So this value is E inverse over 1 plus E inverse, and this value is equal to E plus 1, which is does not converges to 0. So we can tell this sequence of function pointwise convergent but does not converges uniformly. So option 3 also wrong option. And option 4, here also fn defined from open interval 0 1 to 0 1, and here the sequence of function x to the power n over 1 plus n x to the power n, and here indicate is not uniform convergent. Is it true? Obviously, since x belongs to open interval 0 1, so fn converges to f equal to 0 function pointwise. Now we have to prove is this convergence is uniform. For this, here also I will use the mn test. Mn equal to supremum of fn x minus fx. For this supremum, here x belongs to open interval 0 1, fn x means x to the power n over 1 plus n x to the power n, and this value is equal to 0. Since 1 plus n x to the power n strictly greater than n x to the power n, then 1 over 1 plus n x to the power n, this is less than 1 over n x to the power n. So multiply both sides x to the power n over 1 plus n x to the power n, This is less than x to the power n divided by n x to the power n. And this value would be less than 1 over n. So, this value is less than 1 over n, and as n tends to infinity, this value goes to 0. So, this sequence of function converges uniformly to the function 0. But here the question indicates this is not uniform convergence. This is also wrong option. I hope my all viewers have understood this type of question. Okay? Oh well. Today I will stop here. But I will highly recommend you please see today's video with pay attention. Because today's topic actually very important for any competitive exam. So, you need to check uniform convergence of sequence of function. This topic actually very important for any competitive exam. So, just I have collaborate each of the example of MN test together for as a review. So, see every part of the example with pay attention. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.